Alrighty, for this video, what we're going to talk about are chemical equations. And um, essentially what we're thinking about here when we're doing chemical equations is we're looking for, or this is a way we express how reactions work. So we're getting into this point where we're going to start talking about doing chemical reactions. Okay. And really the chemical equation is a symbolic representation of that chemical reaction in terms of chemical formulas. This is like the language of chemistry. How do we uh, do these things and how do we write these things? Okay. So every chemical equation has two main parts. We have the guys on the left, which are known as reactants. Okay. Sometimes substrate or starting material, all these things kind of mean the same idea, but it's what's going into the mix as you're doing stuff. The stuff on the other side is the products. Okay. So we have reactants, we have products. In the middle, we have this reaction arrow, and the arrow is telling us what's happening. It's saying this stuff over here is being converted into this stuff over here. Okay. You can think of the arrow as the action of the chemical reaction itself happening. Okay. Um, there are numbers in the front, and we're going to talk about this and where these come from. The numbers in the front here are called coefficients. Okay. And they uh, tell us, for this example, we have 2 sodium in here and 2 sodium chloride here. Okay. And we'll talk about where those come from in a minute. Additionally, well, crud, I went the wrong way. Additionally, we will see other things marked in our equation, such as phase labels. Okay, phase labels tell us what state of matter the things in the equation are. Okay, there's 4 of these we will see regularly, and that is gas, liquid, and solid, and aqueous. Solid, liquid, and gas uh, makes sense. We've talked about solid, liquid, and gas before. Aqueous is this thing we've not talked about yet. This just means dissolved in water. Okay. And we're going to talk a lot about things that happen in chemistry as we're that happen in solution, right? This is in solution. Okay. For now, we're not going to stress too much about phase labels. And when we're talking about writing equations, they start to kind of get in the way. So we'll slowly ease ourselves into that. Also, you might see a little delta symbol or a triangle above the arrow. That's going to mean that reactants are heated. Okay, so here what we're saying when we look at this equation is we're going to say that we took 2 sodium nitrate solid, this got heated up, and while it was heated up, it decomposed into 2 sodium nitrite, and some gaseous oxygen was coming off. Okay, and we're going to get our hands into reading these things as we go. Okay, so the biggest thing we want to remember about chemical equations is that they represent real life. And since they represent real life, they have to be what's called balanced, which means they have to obey the law of conservation of mass. Okay. Um, and all this means when we're talking about balancing and the law of conservation of mass, remember, matter can't be created or destroyed. That's what we're saying here. Or we can say that uh, as you're doing a chemical reaction, the total mass stays the same. Okay. And the way we make sure this is true when we write our equations is we're going to say that, uh, sorry, brain fart. We're going to say that the same number of atoms that went into the reaction have to equal the number of things that come out of the reaction. And this has to be true for each element. So when we look at this equation we have here, we can see by looking at it, it's not balanced, right? We have 1 lithium on the reactant side and we have 1 lithium on the product side. That's okay. Our product side has 1 bromine, but our reactant side has 2, okay? Because we have this 2 here, we're gonna need to balance it on the right side. So 2 bromines there. We can only do this by adding coefficients, okay? You cannot change the subscripts, okay? Um, So we've put this 2 over here, that fixes the bromine, but it also messes up the lithium because now there's 2 lithium over here. So we're gonna need a 2 over here to fix the lithium. And now it is balanced. Okay. Things to remember, we're never gonna change the subscripts, and we always want to have the lowest whole numbers possible. Okay. So we want to have the lowest whole numbers possible, and we want to have uh, yeah, the lowest whole numbers possible, and we want to not change the subscripts. All right, changing the subscripts changes the identity of the chemical, and we don't want to be doing that. Okay. All right. Now, the rest of this, I just want to work some examples. I want to show you some tips and tricks to help us get through this. My first tip is if we're looking at something and you see polyatomic ions, and our thought here is if you have polyatomic ions that are present in the reaction and it's the same thing on both sides, right? So here we can see there's a nitrate here and there's a nitrate here. Okay, so there's a nitrate that went in and a nitrate went out. Okay, because a polyatomic ion acts as a single ion unit, okay, because of that, we can balance it just like it's an atom. And so we can balance a nitrate as if it's one thing because it's acting as one thing. Okay, so when we look at this and we want to balance it, we can say, okay, well, there's 2 nitrates on the lead nitrate here. There's only 1 nitrate over here, so we're going to need a 2 there to balance it out. And just like we saw in the previous example, we have a domino effect. Putting the 2 here for 2 nitrates also gives us 2 sodiums, which means on the reactant side, we need 2 sodiums. Okay, this also gives us 2 chlorides. On the right side, we have 2 chlorides, so this is good. Okay, so keep an eye out for polyatomic ions. They just have to be the same on both sides. If they're not the same on both sides, you're not going to be able to work your way through it. Or you're not going to be able to do it this way. You will be able to balance it just by counting all the atoms. Okay. Uh, Another thing is if you have an element or an atom that shows up in lots of different formulas in the equation, we're going to save that for the end. So here we have oxygens there, oxygen there, and oxygen there. Okay. It's going to get really tricky. Eventually you could do it, but you also run the risk of what I call balancing in a circle. You're stuck in a loop and you never get it to balance. And if that starts to happen, you want to like clear your brain out, wipe it over, start over, and come back and leave the one that's everywhere for the end. And I bet you, if we balance everything else, it's going to come out. I would say it comes out magically right, but it's just because that's how it works. Okay. So let's take a stab at this. We want to start with whatever has the largest subscripts, the most subscripts. Um, Here, let's start with this P4. Okay, we have 4 phosphorus on the left. We have 1 phosphorus on the right. So that's going to require us to stick a 4 right there. Okay. Now, putting the 4 here gives us 4 of this phosphoric acid, but there's 3 hydrogens here. So this is a total of 12 hydrogen. If it helps you to make a list of how many things are in each one, do it. Okay. You'll have plenty of room to write. You can always flip stuff over and go on the back, right? Make notes, keep track of this. Okay. So if we have 12 hydrogen on the product side, we're going to need 12 hydrogen on the reactant side. So that means we need 6 waters because we have a 2 here. Okay. Now, let's go back. We've done everything except for the oxygen. We want to count up on our oxygen and see what happened. Okay. Our left side has 10 plus 6 because the 6 can apply to the oxygen as well. So that's 16. So our question is, does that equal, what do we have here? We have 4 times 4, that's 16. So that checks out. We didn't actually have to think about the oxygen because we saved him for the end. Hydrogen is another one that shows up a lot of times in many different formulas. And so you want to make sure um, a good idea is to leave that for the end and it should work out. Okay. Okay. Here's a big example. This one's going to do a lot of things, and I'm going to try to remember to tell you some tricks and stuff as we go. Okay. First up, let's look for polyatomic ions that are the same on both sides. Okay. Right off the bat, I can see we have a sulfate right here, and we've got a sulfate right here. Okay. So that's a good trick we can use. Thing with a lot of subscripts, the good place to start we're going to start over here with the iron 3 sulfate and get that started. Okay, so let's balance the iron. We have 2 here, we have 1 here, so we need a 2 on the right side. Okay, now we're going to come back to the beginning and balance the sulfate. There's 3 on the reactant side. There's 1 over here, so we're going to put a 3 there. All right, now we've got a bunch of stuff all over the place. I'm going to kind of show you, I saved my note up here is to break up the pieces to be easier. You can totally do this by counting the atoms and finding your way through it. I find it a little bit easier if we think about it as pieces. Okay. If you look here, we have water and we have OH on the other side. If you have water and OH together or hydroxide, we can think about water as H and OH, and it will be easier to balance. Okay. We also, if we look, have ammonia, NH3, and we have ammonium, NH4. This is another one we can break up and say, this is, ooh, I don't know what just happened there. NH, let me erase this. This is the same thing as saying we have H, NH3. This isn't really what things look like, but it's a way to think about it in terms of making the balancing a little bit easier. Okay. So if we look, we have one NH3 on the reactant side. We have 2 NH3s on, well, 2 times 3. So we have 6 NH3s on the right side. So we're going to use 6 right here. We can do the same thing with the waters, right? We have 3 hydroxides times 2. So that's 6 hydroxide on the right side. So we need 6 hydroxide on the left side. This is only 1 hydroxide. So we're going to put a 6 there. And if we think about it, the hydrogens that are loose are going to balance themselves, right? There's 6 loose hydrogens here we didn't pay attention to, and there's 2 a single hydrogen times 3. There's 6 hydrogen over here that we didn't pay attention to, and they balance themselves out. Okay. Um, if that was too messy, let's go back, and I'm going to rebalance this. I'm not going to erase it, but I'm going to rebalance it without doing the breaking stuff apart. Okay. We're do the same thing. We have a sulfate and a sulfate. So we're going to need 3 NH42SO4 down here. We have Fe2SO43. We have ammonia. I should have printed this twice, but it only struck me as now as I'm doing this that we might want to do it both ways. Okay. There we go. All right. So we balance the sulfates. That's good. We're going to come back and balance the iron. So we want a 2 here. It's the same way we did in the beginning in the other one. Okay. That's everything we can do that way. All right. Everything else we're going to do individually. Since hydrogen shows up all over the place, there, 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 and there, we're going to save hydrogen for the end and balance the other stuff. Okay. Nitrogen is next in the equation, so we're going to use nitrogen next. You could do oxygen next if you wanted to. 2 times 3 is 6, so this has 6 nitrogen, so we're going to put a 6 here. Okay. Here we have oxygen and oxygen. So this is 3 times 2. This is 6 oxygens. So we need a 6 here. Okay. Now we have filled in the coefficients. We can look at how many hydrogens we have and see if we did okay. This is 6 times 3. So this is 18 hydrogens. This is 6 times 2. So that's 12 hydrogens. That has to be equal to 3 times 2, which is another 6 hydrogens. 2 times Here we have 2 times 4, which is 8, times 3 is 24, and 18 plus 12 is 30 hydrogens, and 6 plus 24 is 30 hydrogens. Either way, you get the same answer, okay? Think it through, figure out a good way to work it for you. Oh, wait, let me do that in a second. Okay, and it'll work out. Okay. Remember, we always say if you can do it forwards, you can do it backwards. So let's try to do a backwards one and think through it. Um, the backwards one is a little bit more challenging because it's going to force us to remember our nomenclature stuff. Okay. So what we want to come up with here is we want to read the sentence and convert it into an equation. And then once we have the equation, we can balance it just like we were doing before. Okay. This one also has phase labels in it, so we'll get a chance to practice with phase labels as well. All right. So we'll just read this through and write as we go. Okay. Solid sodium metal. So sodium is Na, and we were told it was a solid, so we'll put solid there. Reacts with water. I'm leaving a gap so we can put a coefficient there if we need to. We can assume water's a liquid unless you're told otherwise. 99 and a 99 whatever percent chance it's going to be liquid. Uh, reacts, this is our verb. Okay, giving a solution of sodium hydroxide. Well, sodium hydroxide is NaOH. Solution, it's going to mean we have something that's aqueous. Okay. And releasing hydrogen gas. So there's hydrogen gas. Remember our diatomic things, so watch out for those. Remember we said no halogens, right? Those are the ones that are diatomic: nitrogen, oxygen, hydrogen, all the halogens. Okay, let's get back to this. Now we've got the equation. Now it's just like what we were doing a minute ago. We just need to balance this dude. Okay, hydrogen's all over the place, so we're going to save them for the end. There's one sodium. Okay, one oxygen, one oxygen. All right, so now we're down to the hydrogens. This side has two hydrogens. This is one hydrogen and two hydrogens. All right, we're stuck. And this happens a lot with diatomics. You feel like you're stuck. This side is three hydrogens total. There's no way we're going to be able to balance a 3 and a 2. We only have 2 on the reactant side. You can't see my hands. You only have 2 on the reactant side. So we have to have an even number on the product side. And the easiest way to do that is to slap a 2 in front of the sodium hydroxide. Okay. Now this is 2 hydrogens, and the total on this side is 4 hydrogens. So if we go back to the reactant side, we can make this have 4 hydrogens by putting not a 4, putting 2 right there. Okay. Now this side has 4 hydrogens. Hydrogen's done. Double check other stuff. 2 oxygens now because of the 2. Well, there's 2 there. There's 2 sodium over here. We need a 2 right there. Okay. So really just 2's on everything except the hydrogen. Okay. Remember your nomenclature stuff. This is going to come back at us. Okay. That's it for this one. I'm going to do another video with a couple more examples. So check it out. Let me know how you're doing. If you need anything, let me know.